The Parton distributions are a probability, the hard process is a probability, so it's a multiplication of probabilities. So it's an approximation. And is in some cases is justified by using the factorization theorems. But that relies on the fact that in the hard process you have to have a hard scale, for example, a particle that comes in the hard in a large perpendicular component, or a mass like this very large, for example, a quark that is massive, hard. And in those cases, you can justify that, but it's an approximation. And I am sort of surprised that it's nobody mentioned this. A lot of work is done in the Parton distribution function, the FG that are included here. A lot of work is done. A lot of work is done in the hard process, and people talk about leading log, next to leading, next to leading, etc. But nobody mentions that this is an approximation. What are the corrections to this picture, the complete picture? I have never heard in any conference, never people mention this. So far, I am the only person that has mentioned this, which is, for me, is incredible. I mean, it's just, unless you know the correction to this picture, it doesn't make too much sense to work so much in the details of the Parton distributions and the hard process. And the thing, I presented this in a Slack, and people that started sort of mentioning things, but they couldn't answer this question. I mean, there were some people that were experts there, but this is, I think, is a very important thing. I mean, that nobody talks about the corrections. The corrections can be sort of in different ways. One way to look at the corrections is that you don't have necessarily only one parton interacting. You can have several partons coming from the same hadron that are interacting, sort of a different process. Obviously, these are going to be down, but what is their size? Nobody knows. With Marat, we consider this type of approximations in one particular case, with the JSI production, and they were important. They were not very, very small, although obviously we have to look at, for example, two-gluon distribution functions and things like that, and we had to do some approximations and some guesses about that. But in any event, this is an important point that usually is not considered. So I'm going to talk about QCD at the amplitude level. What I'm presenting here is QCD not at the amplitude level. I mean, we will consider these blobs here, and this is not a Feynman diagram. Only the hard process is calculated as a Feynman diagram, but the rest is not a Feynman diagram. The distribution functions are really probabilities, so they are not really Feynman diagram. So I'm going to talk about three things that are going to sort of they can be related to QCD at the amplitude. And the first one is violation of the momentum sum rule in nuclei. So let's talk about the momentum sum rule. The momentum sum rule comes from the Parton model, really, and it can be justified. Is obviously for the Parton model in which you have collinear approximation, and it can justify using the operator product expansion. You have here the handbag diagram, and the idea in the operator product expansion that the currents that you can see in the upper part of the blob here are very close, at very high Q square, and the currents are very close. So you can, the product currents can be expanded in terms of local operators. And in that case, you can justify this momentum sum rule. But it's not a basic thing, or QCD. I mean, it's just a part of model result. And if you look at the graph here, this is a famous EMC effect, in which they put the cross section for example, iron divided by deuterium or something like that. Then you can see that if you integrate this, it looks like the moment of circle could be valid. I mean, people use it even to predict. You have several regions here. For example, the shadowing region, in which a very small x, you can see that this ratio goes to below 1. And this you have what is called anti-shadowing, etc. And people use the momentum sum rule to justify this type of behavior here. So I'm going to talk about why this sum rule is not correct for nuclei. Actually, it's not even correct for the proton. The other day there was a talk a couple of days ago by I don't remember his name, but also in his the way he was presenting the momentum sum rule was not valid for his approach. And also Al Miller has proved that even for the proton is not valid at very small x. But in case of nuclei, this is the result. I mean, at very small x, you can see that it's a shadowing there. I mean, this ratio is less than 1. Then you have the anti-shadowing. The red line is for electron scattering. The blue dashed line is for neutrino scattering. So the idea is that when you have deep penalty scattering nuclei, and in the frame in which the nucleus is at rest, you can see the scattering as you can see the picture there as a production of a QQ bar pair. And the QQ bar pair interacts in 2 ways. It can interact in 1 step, with 1 nucleon that's called N2, 1 step, and it can interact twice, interact in N1 and then in N2. I mean, so they're and this process interact is quantum mechanics. I mean, so both processes interact, interfere, and interference gives you anti-shadowing and shadowing, both effects. So the idea is that since we're very small x, you can apply what's called Rayleigh behavior for these amplitudes. And here I am putting the different phases that appear. If you are not familiar with the Rayleigh behavior, that's not really important. It's the fact that you have this interference of 1-step and 2-step processes. And then it means that the operator pro expansion is no longer valid. I mean, even the 2 nucleons are separated, so you cannot put the 2 currents very close. So you cannot have a locality of currents, and it's clear that the momentum sum rule is violated. You don't have a momentum sum rule in this case. So that's the one thing. The next things I want, and these are the result of the calculation. I mean, the calculations give you a good result if you put everything together. Anyway, the next thing I want to talk is another process that's very important. Actually, this is, we did that some time ago. It's called single spin asymmetries. Actually, this paper has like close to 900 citations in Spires. And it's very, very well known. And I even have a story about this paper, because we sent it one day in the morning and was accepted like 5 hours later. It was sort of a record. We sent it to Howard Georgia, and the editor of Physical Letters, and he accepted immediately. That was sort of a record. I mean, it took like 5 hours to be accepted. Anyway, what does it mean? It means the following. When you have an interaction of an electron with a proton that is polarized, you can have the proton and produce, for example, a pion. You can have the proton polarized two ways. I mean, like it's given in the picture there, no? With the proton polarized transversely in the direction of the plane, I mean, inside or outside. And the difference gives you what is called single spin asymmetries. And at that time, when we were writing the paper, there was the idea that there were experiments, but the idea was QCD could not explain this. It was impossible for QCD to explain this. It was a problem with QCD. And we showed that that was not the case. So let me give you the main ideas of this. The first is that we change bases, and instead of using transfer speed, we're going to use helicity bases. And you change that, then it comes out to be twice the imaginary part of this interference between the case in which the proton has helicity plus or has helicity minus. And then I haven't put there the final state, but the idea is that then you have two spin amplitudes connected to the same final state. Yeah. One is helicity flip and this is non-flip. And this interference, like I said, the imaginary part of the interference that is two amplitudes. So it's clear that this is QCD at the amplitude level because we are talking about amplitudes. Yeah. And we need the imaginary part of that. So that means that it cannot be a tree level, because at tree level, the imaginary part is going to be zero. So that means that you're going to have what is called finite state interaction. So the physics of this is that we need the finite state interactions of the quark that is interacting in order to explain this type of asymmetry. This is very similar to the anomalous magnetic moment. Actually, I wrote another paper with a Chinese colleague about the connection of these asymmetries with the anomalous magnetic moment, F2 of 0. So this is the main, the other thing that I wanted to mention that gives you a handle of QCD at the amplitude level. Recently, with Valery Lubovinsky and Stanley Brodsky, we produced a paper in which we calculated this using a quark-Kähler dipole Fock state moment in which we use lifelong wave functions coming from ADS QCD. And these are sort of the results. And I can show you. I don't want to go into details, but this is not so difficult. This is just a model. So it can be calculated very easily within the model. And we use lifelong wave functions that come from ADS QCD. ADS QCD, as you know probably, is a very useful tool for having some lifelong wave functions for different Fock states. It's an amazing thing. I mean, and just as just one thing, these results are very consistent with results coming from other people. So that's very important to show, to mention. ADS QCD, this is a sort of a parenthesis here I want to mention. So it's important to mention something about ADS QCD. ADS QCD is, the idea is that we use what is called the Mandacena conjecture coming from string theory about the connection between a gravitational theory inside a certain volume with a gauge theory in the surface. It's really an amazing conjecture. I mean, but it comes, you can show that it comes from open and closed sort of strings. So you can view interaction of branes like open and closed strings and come from there. We use this in this case of QCD is used in less dimensions. It's in 5 dimensions, and the surface is 4 dimensions, and QCD is supposed to be in 4 dimensions. So we use the effective theory inside, which is a gravitational theory, in order to have some idea of QCD in the surface. With Valery Lubovinsky, we use this in order to get the form factors of the plot of the deuteron. These are the results. I want to show you this just that you can appreciate the power of this ADS QCD. There are only 2 parameters here. One is the mass of the deuteron, which obviously can be fixed by the mass of the deuteron. I mean, so it's not really a free parameter. And the other one is a scale parameter that is fixed by the nucleon case as half of that. So it's very reasonable. And with that, we get this result. For me, it's amazing. I mean, I don't know any other approach in nuclear physics anywhere that can give you these results for the deuteron form factors. I mean, usually the deuteron form factors are sort of obtained in very complicated models with sort of lot of interactions and everything, and sort of it's very complicated. And this is very simple. It's very simple. I mean, say that I don't really understand why it works so well. No, because I can give you this is the other thing. No, the original conjecture was about n, what is called n equal to 4 super young meals, which is not very similar to QCD, and I can show you several things that are not really the same. For example, n equal 4 super young meals is not confining, doesn't have a chiral condensate, have a continuous spectrum, etc. It's conformal, and QCD doesn't have these properties. So for me, it's amazing that it works so well, but I don't understand why it works so well. Although other people that use that, they're very excited about the result. But I would like to understand why this works so well. This is just a parenthesis about this is ADS QCD. And the next result is the following. Sort of heavy quark electron production. So the idea is you have electron proton and you produce a pair of heavy quarks. There have been a lot of people working on this. I mean, actually, there was a talk by Benjamin Guillot in which he mentioned that. And in the talk, I came out with the question. I mean, why don't you have interference? You know? Because they had, in the talk, he showed that there were 2 different final states. No, the same final state, but different sort of intermediate state. And in that case, obviously, for just from quantum mechanics, you have interference. So we are doing that with Valery and Stambrowski, because you can think that you have 2 contributions. And this is very interesting because you have one contribution from the Fock state in which you have quark, anti-quark, that is, you can see the graph below. And the other one, Fock state, in which you have UUD and a gluon. As you know, the proton has many Fock states. I mean, they have the usual valence part, UUD, but it has also another Fock states in which you have, for example, the gluon, you have a QQ bar, etc. And in this case, you have contribution from both Fock states. It's the first time in which this has been appreciated, I think. I have never seen something like that, sort of interference, because they are going to interfere, because they produce the same final state. These graphs are not the same as the one at the beginning. These blobs here are wave functions. They are not sort of Parton distributions. They're completely different. I have to be careful about what do you mean. What do you mean? So this can be calculated also using the same approach, ADS, QCD, and we are working on that right now. And we came out with, I'm going to show you this result. I mean, the result, this is a cross-section in terms of Q square. It works rather well. There is one thing, one caveat, which is that the normalization is put a little bit by hand, no? But the behavior is very good. No? Anyway, this is the next thing I wanted to talk about. ADS, I mean about the QCD at the amplitude level. And these were the main things. No? In all these things, we are dealing with amplitudes and not with this hard scattering model that I mentioned at the beginning. So moving on to the next subject, I'm going to talk about what is called diffractive deep inelastic scattering. So it's the same deep inelastic scattering in which you interact with a lepton with a proton, and produce, and the same lepton appears in the final state, and the rest is you don't measure sort of dx. This is the usual deep inelastic scattering. One is nothing new, but this includes what is called diffracted deep inelastic scattering. What does it mean? It means that it includes part of the sort of results of the events. The events are diffractive. That means that they are high energy but low momentum transfer to the proton, and this can be shown in the graph on the left. So the proton really doesn't break up; it remains a proton, and it's a sort of a Pomeroy exchange there. I mean, it's sort of you can think of the Pomeroy as several gluons interacting there. So part of the cross section comes from these processes, and obviously, looking at the process, it's clear that you are not probing the proton. These are not part of the proton. If you want to learn about the internal structure of the proton, these events are irrelevant. So this should be subtracted. That's it. No, that's the main idea. That this should not be considered as probing the proton itself. It's a very simple idea, and here is in more detail. Usually, when you have this, the graph on the left is that you have, like I said at the beginning, you have this product of currents, and when Q squared is very large, the product scatter is very close, x minus 1 squared going to 0. The operator product expansion, like I mentioned at the beginning. So you can apply it. But in this case, when the proton stays in SAC, and that's the graph on the right, then you cannot take the limit in which the currents are very close. So there is no exponential expansion. No, that's another way of looking at that, very similar to what we said at the beginning. So these events have to be subtracted, excluded. And this is more or less, this is probably the only transparency in which I'm going to show some formulas. So the whole idea of the formula is that you have to, in order to have the real sort of distribution functions, you have to subtract the diffractive distribution functions. And here is sort of the idea how the evolution of this. We are assuming the C that appears in this formula is the evolution. The evolution is assumed to be the same for the deep inelastic or for diffracted deep inelastic. Any case of diffracted deep inelastic cutting, you have the Pomeron and Ray, etc., and you have to subtract those. So it's not very very difficult. So the next is the last thing is hidden colors in nuclei. So we are going to talk again about this EMC effect. This effect is been going on for a long time, and there are many explanations. For example, I am showing you here one that I don't see the date, but this is a long time ago also that we did an explanation with Peter and Molly, in which we use a relativistic model and without any parameters, and we could explain it, no? Sort of a convolution model. We could explain that. And there are many other things. Not many people pay attention to this, but I think it was a rather good paper. But anyway, yeah. But here I'm not going to talk about that. I mean, this is just to show you that when this appeared, it has been going on for many years, there are many explanations about the DMC effect. But I'm going to mention something different. The fact that people have talked about inside the nuclei, you can have what is called short-range correlations. And this is a transparency from a conference in which somebody was talking about this short-range correlation. What does it mean, this is short-range correlation of nuclei? This is it. So the experimental result show, and this is the paper of the experimental results, show that in the final state, you have predominantly proton-neutron sort of coming together. So not proton-proton or neutron-neutron. So somehow there is a correlation between that. There are people that have worked in that. For example, Claudio Scioffi, for many years have worked in that to have these short-range correlations. But we are going to have a different approach here. The idea is what is called the extra diquark model. So we are going to do the following. Oops, no, not yet. We are going to do the following. The idea is to think about, because you have this correlation between proton and neutron, we're going to assume there is correlation also between the U and the D quarks inside the proton. So the valence part of the proton is going to be a U and a UD sort of a pair. Obviously, the pair is going to be in a 3-bar color state in order to give you a singlet when you multiply by the 3. So the idea is that we are going to have what is called 6 of these diquarks producing a bound state. So now we are going to form that. What is the construction? And this is going to be a completely new nuclear Fock state. They have never been considered before. So the first step is the U and the D, forming what we call a diquark. And that produces a C and the 3-bar. And the 3-bar is antisymmetric. And we want antisymmetric because this is a they are fermions, so we want the antisymmetric part. Now we go to the next step. And the UD, one sort of these diquarks is going to be sort of get together with another one. And it's going to form a dual diquark. These are effective bosons. So the 3-bar plus 3-bar, we want the symmetric part, and that's a C-bar. A C-bar. And now we go to the next step. The next step is to take these dual diquarks and get them together. And get them together is going to be a 6-bar times 6-bar times 6-bar, and this gives you a singlet. So this contraction is the contraction of the extra diquark, which gives you a singlet. The nice thing about this is that this has exactly the quantum numbers of the alpha particle. It's helium nuclei. So it's a new kind of construction that could be very important for nuclear physics. We have to remember that the helium, the alpha particle, the helium-4, is a very special nuclei. It has a tremendous binding energy that has never been explained correctly. The states, and presumably also this extra quark component. For example, even the helium is going to contain probably both. In order to have a better feeling of that, we're going to do a sort of a rough calculation of the color effective charges. No? Just taking only one gluon exchange, no more than that. Just one gluon exchange. Effective is 3 color charge. So the color factor is given there. I mean, it can be calculated, and in terms of Casimirs, is given in the second formula there. When you have you're composing something, is the Casimir of the components and the Casimir of the result. And it's very easy to calculate then the different color charges for these different configurations I presented before. And in the table on the left, you can see the results. The results are, for example, 3 + 3 bar gives you, is attractive, 3 + 3 is, etc. And the interesting part is that if you assume that the heavy die quark has only 2 body interactions, then the 6 + 6 + 6 to go into 1 is very, very attractive, tremendously attractive. I am assuming that it's only 2 body interactions, but it gives you a tremendously attractive color factor. So that a little bit sort of reinforces the fact that this is a really an energy interacting bound state that can really happen. Obviously, you can have other things like 3 body interactions that could be present, etc. This is just a rough idea of what's happening. Now, it has many. We haven't really gone into the details of this. I mean, the phenomenological consequences. I mean, it can happen many other things. That, yes, for example, you are going to have, like I said, important. They're going to be important for nucleus greater than 4, etc. So many other things are going to happen. But we have to work out a little more than the dynamics. I mean, obviously it requires model and all that. But it could be important in general in nuclear physics. And a test of that, of this type of ideas, can be done what is called diffractive dissociation. What is that? Diffractive dissociation, and this was done by Ashery some years ago. Unfortunately, he passed away. But his idea was to have a beam, and he used, for example, pion beam against a nuclei, and have an interaction, high energy interaction, but with not so much momentum transfer. So it's diffractive interaction. And in that case, there was a possibility that the pion would diffract and would dissociate into jets. So the quark anti-quark structure of the pion could be tested rather easily. And it was proved that this really was a measure of the momentum distribution of the wave function of the pi. And the separation, the parameter separation of the quarks is inversely proportional to its relative transformation. So, for example, you can have diffractive dissociation of the proton. And you can show whether, I mentioned before, you see, that one important possibility was that there was a correlation between U and D. So it's possible that you can have both possibilities. I mean, to have three quarks coming as jet, or to have two only. And what could be a UD? So you can test this type of ideas using this diffractive dissociation in the case of the proton. And the same diffractive dissociation in nuclei. You can do the same for the helium-4, for the alpha particle, and test whether you have more possibility to have a neutron-proton, or proton-proton, or neutron-neutron, to have this correlation, to show that there is a correlation between neutron and proton compared to proton-proton and neutron-neutron. It's the same, the same idea applied now to the alpha particle. Moreover, you can also, with the alpha particle, test the possibility of having this duodide quarks, also. See where you can excite these duodide quarks. So there are several possibilities of testing the ideas that they mentioned using diffractive dissociation. Also for the deuteron, you can have similar, you can, in the case of the deuteron, for example, also see the possibility of looking at of these dichords coming out of the interaction of diffractive dissociation with the nucleus. And you can even apply to electromagnetic systems like atoms and etc. No, so I think this is it. I have shown different applications of QCD. I haven't shown the details. If in the future somebody of you would like to talk to me about the details, I can obviously, no problem in giving you details of the papers and etc. Everything here has appeared in several papers. The main collaborator has been Valery Lubovinsky, and other people too, Marat, etc. And I think I have shown you that there are few places in which you can really test QCD at the amplitude level. I think it's very important to look into that. I'll show you three examples of that. And the next thing was deep lattice scattering, diffracted deep lattice scattering, the fact that you have to subtract these diffractive events from the usual distribution functions. And the last thing was a very novel idea of having these extra dichords which have the same quantum number of helium, and I think could be important in understanding several processes in nuclear physics. So this is, thank you so much, and I remember you that we are going to have an important conference in next January at the university. And so I hope everybody is going to attend. Questions, comments are welcome.
Thank you very much, Professor. Thank you very much for a very nice talk. Alfonso, please go ahead.
Thank you, Ivan, for this very nice talk. about the violation of yeah, about the violation of factorization.
The general thing.
Yeah, yeah, the very first topic.
Yeah,
this one, your paper with Marat. It was about the production of type C. This production has yes. This diagram is very similar to the production of the Higgs bosons at the LHC. At the energies of the Higgs, such corrections would be important for the production of the Higgs, or they are suppressed because we are in the perturbative regime.
Well, that's exactly what I mentioned. I mean, that's exactly the question. I don't know, and nobody knows, and that's exactly the problem. You are putting exactly the problem. Nobody knows. Nobody knows. People don't know what are the corrections. They don't care, it seems to me. They never mention there are corrections. They mention this is, well, they have two gluons, and the gluons, and you have the top sort of loop, the triangle top, and you produce the Higgs, but they don't mention the corrections. Actually, I remember that it was Lance Dixon, which is in the talk Slack, and he said, well, but the corrections are no at 1 over the last square. And he said, well, what's the coefficient? And he didn't answer that. No?
Yeah,
So
okay.
nobody knows. That's a very good question, but nobody knows.
But you were able
That's
to estimate the correction for the type C.
Yeah, but
would it be possible to repeat that for the Higgs?
It's possible. It's possible. But remember, I mentioned that this thing that we did contains very unknown things. For example, the two gluon distribution functions, and we had to guess a little bit there. I mean, sort of what to put and all that. You know, it's not a rigorous thing at all. Yeah. It's just an approximation. I mean, it's just to see sort of order of magnitude, I would say.
I see.
That's a problem. Nobody knows. It's a very hard thing. And actually, I remember after the talk, there was a guy there and I asked him from Austria, and I asked him, so what do you do? And he was very shy and said, well, I am doing what Ivan mentioned. I mean, the corrections to the hard scattering.
Next.
Apologizing. But that's a problem. I mean, no, I insist. I have been the only person that I know that have mentioned this. It's incredible. And it's used all over the place.
Yeah, thank you.
Yeah, Will.
Yeah, you mentioned your work in the anti-shattering region, which you explain by the interference between the Reggion production and the Pomeron production.
Yeah.
I'm wondering if it's possible to guess what could be the effect in a polarized measurement of that process. Because in the not so distant future, we have an experiment that is going to do that.
That's a good question. That's a good question. We haven't discussed, and I have to confess, I am not an expert in sort of Rayleigh trajectories and Rayleigh exchanges and all that. So in this case, I rely on Stambrowski for the contribution of the regions and etc. From different quantum numbers. And I guess in the case of polarized, it's a very good question. I mean, it has to be worked out, and probably there are other trajectories that contribute. I think it was Bjorkin that mentioned that polarized sort of processes were the graveyard of many models. I mean, that's what it was.
Well, I asked Stan the same question and he said he didn't know, but he would think about it. And that was a long, long time ago.
Okay,
So,
sorry.
but I'm hoping people, well, it's never been measured so far, but we're
Yeah.
going to measure it. And so
Yeah.
now it's a good time to predict it.
Yeah, sorry, but yeah, you have to work out and to see what are the ray trajectories that contribute and everything. You know, that.
Any more questions from the audience?
Claudia has always questions. I mean, Claudia should ask any.
Well, there was a simple question that I had, but
Yes.
when you put the sum rule, the momentum sum rule, you put this letter psi or xi or something. This is x, right?
Yeah,
Here.
yeah, you can put it whatever. It's a variable. Yes.
Okay.
Yeah.
In
Usually sec, right?
Yeah. Okay. So this is a Feynman x or something like that, right?
Yeah. Well, it's a momentum. Yeah, right.
Yes.
In deep elastic scattering, the Feynman X, the Bjorken X, yeah.
My own question was, this is a simple question. The other question was, when you talk about diffractive, diffractive means that the momentum transfer is small or what?
Yes, yes. It's a high energy, but the low momentum transfer.
So still you have, say, the proton or whatever you're hitting, it dissociates.
Is what?
I mean, this is not the same as a elastic scattering. I mean, the initial proton or the initial hadron, whatever, it dissociates, or it gets destroyed. It's not, does not appear in the final state, no? Well, let's see, where is it? Not here.
Yeah, here. So the exchange, the part that they have to do with the Pomeroy is not large transfer momentum. Also, this is the X here carries most of the
but the proton remains in the final state.
Yes, that's the idea.
Can you go to the next page, because
so you have look at the figure on the bottom. You have a what is called a rapidity gap there.
Yes, but yes. Can you show me the next page? No, it's not this one. It's further, probably.
Well, I don't know which one.
It was near the hexadichloric, wasn't it?
Yeah, it was around here a bit further.
No.
It's where you talk about also nuclei or the helium or something.
Yeah, I don't know which one I talk about. No. Was in the
somewhere you had helium, also helium-4 and things like that.
Yeah, helium-4 here. Here, diffractive dissociation.
I think it's around here. Yeah. So yeah, here. So here. You went too far. You went too far.
Too far?
Yes, one page less. Here. So there. So for example, the bottom line where you have the helium-4. Here, A is what? A is some nucleus, right?
Nucleus that can be excited.
Yeah. And the A prime is the same nucleus.
Yeah, it can be like A. No, A is the nucleon that the target nucleus, and A prime is just can be excited nucleus. It's the same nucleus, yes.
Okay. So the idea here is that the helium is, say, somehow destroyed, and you have these two protons, and then whatever is in the X.
Yeah.
But the nucleus that you hit remains intact.
Remain more or less exact, yeah.
Okay, I see. All right. Thank you.
I have if I can ask now, a question about the hexadiquark.
Yeah.
Is it possible to estimate its size? Because intuitively, I would have thought it is really small compared to the helium nucleus. And that could be detected experimentally by a reaction in a bigger nucleus.
Yeah, well, you have to have a sort of a dynamical model for that. I mean, that's part of the problem. I mean, in the case of the main idea is that take helium-4, you're going to have both configurations probably, not only the hexadiquark, but the other two and two. So we haven't gone into the details of the model. It's just the fact that it should be there. It should be there, this thing.
Mm-hmm.
But the details, what's the importance and everything, have to be worked out. I mean, it's just so far, it's just an idea. There is no reason why it shouldn't be there in nuclear physics. No. For example, if you do deep energy scattering in the nucleus, probably you're going to have quasi-elastic peaks for 4, 8, etc. No, that could be one consequence of this. You can think about consequences of this, but to have a dynamical model, it would take some time, obviously.
Well, it's interesting to talk about the quasi-elastic peak for the diquarks.
Yeah. Yeah.
We can look for that.
Mm-hmm.
So I have a question that just where you're showing there, you have this pion hitting the nucleus. This is diffractive, say. So you have a QQ bar, and then you have the same nucleus and X. Why would this give you some information of the wave function of the pion?
Because of the idea is you can measure the distribution in momenta, and that can be related to the wave function of the pion. The distribution in momenta, you know?
The distribution of momenta of what? Because you have QQ.
The produce quark anti-quark.
Yeah, but how do you see the quark?
Relative momenta.
It's the PT distribution of the jets, the relative PT distribution, I think, isn't it?
Yeah.
Okay, so you have these two jets that do not get confused with all the X there, huh?
No, yeah. The X probably in this case is probably not going to be maybe even there, you see, because
I see. So in the case that you have, say, a harsh scattering process, you have the pion hitting the nucleus and you produce all kinds of things at the end, then you will not know any information. But the point is that the nucleus remains intact, and then you have these two jets. That's the idea.
Yeah.
Okay, I see. Okay.
Any more questions from the audience?
And this happens very often, or is a small fraction of all the collisions?
Well, I haven't seen the details. I have to look at details of the paper I think in the case of the pion, it's probably very often. I mean, when it brokens up, you can see probably two jets.
I see.
More questions from the audience?
Yeah, I mean, I was asking for this because this sounds to me, I mean, if you have, sorry to take again word, if you're studying, for example, showers in the in the atmosphere because of cosmic rays or something, I would imagine that these diffractive processes are more common than, say, head-on collisions or something like that. So this could appear there, right?
Of course, you're going to have those.
Mm-hmm.
Diffractive, also scattering, yes. Yes, definitely.
I see.
Okay.
Okay.
Thanks a lot, Professor Ivan, for the very nice talk. If there is no more question, we meet at the next seminar.
Okay, thank you.
Thank you.
Thanks a lot.
Thank you.
Okay, bye-bye.
Bye.
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 Bye.